Hello everybody, welcome back. In the last lectures we studied Bose-Einstein condensation, and so we have seen how to detect this phase transition with ultra-cold bosonic atoms, and you know that of course the quantum world is made by bosons, but it is also made by fermions. So this will be the topic of the first part of this lecture. So I will speak of ultra-cold Fermi gases, and I will be quite fast because of time and because we want to also to discuss other topics in this course. So if you are interested in this topic, I invite you again to follow the course Gas Quantistici, in which the physics of bosons, but also the physics of fermions will be treated in quite large detail. So today I would like just to touch a few points, and the first point that I would like to touch is very experimental. So how can we produce these ultra-cold Fermi gases? That are, of course, the analogous of an ultra-cold bosonic gas. With the difference that, of course, in the case of fermions, as we will see in a moment, you don't have phase transition as you have in the case of bosons. So you don't have a Fermi condensation. Let's see. But before that, let's ask ourselves, so what should we do in order to realize an ultra-cold Fermi gas? So one could think, okay, I use the same technique that I've used in the case of bosons for Bose-Einstein condensate. So I perform laser cooling, then I trap my atoms in a magnetic or in an optical double trap, and then I perform evaporative cooling. Good. There is only a problem. So in the case of identical fermions, evaporative cooling does not work. It does not work because we have studied some lectures ago that if you have a gas of identical fermions, ultra-cold identical fermions, you cannot have collisions between the particles. Because of a symmetrization of atomic wave function in the scattering process, at low energy, S-wave scattering is forbidden, and so you cannot have this process that is essential to the physics of evaporative cooling. So in other words, if you perform evaporative cooling with an ultra-cold gas of identical fermions, so you can evaporate the gas. So you can remove the particles with higher energy, but the remaining particles will not thermalize because you cannot have collisions between them that allow you to reach a lower temperature, so that allow you to reach a new equilibrium state. And so what can we do? We can make a small variation on the theme of evaporative cooling and perform what is called a sympathetic cooling. So what is sympathetic cooling? I will show you with a slide. And the whole idea of sympathetic cooling is rather easy, because it looks much like evaporative cooling, with only difference that you're not just cooling one gas, but you're cooling two gases simultaneously. And why is it like that? So let's consider this scheme. So here we have a trap, and in this trap you're trapping two different chemical species. So a gas, for example, of potassium atoms and a gas of rubidium atoms. So first, of course, you have to laser cool both of them, so with different lasers or with different modes, and then you trap them in the same either optical or magnetic trap. And here, one of the two gases is the gas that is interesting for you, is the gas that you want to cool for your experiments. Let's suppose that here this gas is made of potassium atoms, for example, fermionic potassium. So this is the gas that has to be cooled. But then you know, for what we have said before, that fermionic potassium cannot collide. So the red particles cannot collide between themselves. And so in this case, we use the presence of the other gas that we can consider as a kind of coolant gas. And we take here rubidium, that is one gas that can be cooled very well in evaporative cooling. And so the idea is to perform a forced evaporation on rubidium, so on the coolant gas. So rubidium will cool, so the temperature of rubidium will decrease. And so now, because of interactions between rubidium and potassium, So we can have a thermalization of potassium atoms that is mediated by the presence of rubidium atoms. So in some sense, this is called sympathetic cooling because you have a sympathy between the two gases, and so potassium cools thanks to interactions between rubidium. So in other words, rubidium mediates the collisions that were absent in the case of potassium only. And this technique is very efficient. Why? Of course, you need to work at the beginning because you need to double the complexity of your experimental setup in order to laser cool to different species. But then you gain in the fact that here you are interested only in the behavior of potassium. So you don't care if you lose rubidium atoms. And you lose a lot of rubidium atoms in evaporative cooling. And here, if you are smart enough, you can perform a cooling of the potassium atoms without changing their number. So just by evaporating the rubidium particles, so you can remove heat from the potassium gas, and so you can lose energy without losing number of particles. And this is very helpful because the evaporation will not touch the potassium atom, so you will not lose density, and so you just gain. And how can we do that? So how it is possible to evaporate just one of the two species? There are tricks to do that. And what is shown here is a trick that you can perform by using magnetic traps. In a magnetic trap, we know that we can trap atoms only in some specific spin states. And the forced evaporation can happen if we make a spin flip transition induced by an external field that flips the spin of the atoms towards a state which is not trappable. And this is what is shown here. So here we are considering the quantum numbers F and F for rubidium. So the 2-2 state is a state that can be trapped magnetically. The 1-1 state is an anti-trapped state. So these are the low field and high field seeking states. And so here the evaporation is performed by applying a microwave. And this is because we are not just changing the MF value, but also the F value. And so we know that in rubidium, the difference between the two hyperfine levels is on the order of 6.8 gigahertz. In the case of potassium, this is very different, because for potassium, the hyperfine splitting is just on the order of 1 gigahertz. And so if we perform this forced evaporation with a microwave at this frequency, so we are just digging a hole in the trap for rubidium, but not for potassium, because potassium is not absorbing microwaves at this in this frequency range. So basically, in this way, we can evaporate only rubidium, and so we don't lose any potassium atoms, and we gain a lot in terms of phase space density for the potassium atoms. And apart from the complications in the laser cooling of two species, so this technique is very easy, in the sense that you just need to pick two atomic species that have good collisions between them, for example, rubidium and potassium, and then you just need a large number of rubidium atoms. So you don't need a large number of potassium atoms, because you don't lose potassium atoms, but you want a large quantity of rubidium atoms because you want a big heat capacity of the gas that you use as a coolant. And so the rubidium atoms should be the large majority of your initial sample. So let me show you some pictures now. And here you see some images of atoms that come from the first realization of sympathetic cooling between atoms of different chemical species that was realized almost 20 years ago here in Florence. And so you see images of rubidium atoms, and you're performing here this forced evaporation of rubidium, and potassium is cooled by sympathetic cooling. So it's cooled by sympathy with rubidium. And actually, this is not fermionic potassium, so this is bosonic potassium, but the technique can be applied in general also to some bosonic species, as potassium-41, that naturally does not have very good collisional properties. So evaporative cooling does not work well for potassium-41, but sympathetic cooling works very well. And so you can see it here. So let's start with rubidium. And so here, these are 4 different images in a sequence of evaporative cooling. And so you see that the number of atoms is reduced, and also the width of the cloud is reduced because this is cooled from 40 microkelvin to almost 1 microkelvin. And so here you see that even if you're not performing any evaporation of potassium, so the width of this cloud is reduced from top to bottom because you have a continuous rethermalization of this cloud with a rubidium cloud. And so you see that basically the size of the two clouds are very similar, but now, differently from the case of rubidium, you're not losing potassium atoms. And so you see that this cloud is getting smaller and smaller, so the temperature is smaller and smaller, but the density is increasing. And so this is a very different behavior. So you start with a very small number of atoms of potassium compared to rubidium, but you throw away rubidium, and so at the end, you end up with something that is similar in the two cases, even if the starting number of rubidium was much larger. So this technique seems to work really well, and this works well also for fermions. And this is the same kind of pictures, but now shown for bosonic lithium and fermionic lithium. Similarly to before, here we are performing evaporation of bosonic lithium, and then fermionic lithium cools by sympathy. And but here you see a difference. So while in the previous case, during all the steps, you see that the cloud always has the same size for the two species, here you see that while it has the same size, more or less, at the beginning of the process, so with for a temperature of 800 nanokelvin, at the end of the cooling, so 240 nanokelvin, the width is very different now. And what you are observing here is really the difference in quantum statistics between bosons and fermions. For relatively high temperature, so the thermodynamics of the two gases is very similar. And so the two clouds will have more or less the same shape, but then instead, here you're observing the difference between fermions and bosons. So bosons can reach Bose-Einstein condensation and so occupy the lowest energy state. Fermions don't. So in the case of fermions, you have the formation of Fermi C, and the degenerate Fermi gas will host a much larger internal energy for the same temperature of the system. So the equipartition theorem does not work anymore when you have a quantum gas. And these thermodynamic measurements were used for the first demonstration of Fermi degeneracy in a gas of ultracold fermions, and this was realized in 1999 for the first time at GILA, the group of Debbie Jean, by using potassium atoms. So potassium 40, in particular, a mixture of atoms in these two internal states was used, and in some sense it is a kind of sympathetic cooling in which you cool one of the two internal states by using the other state as a refrigerator. And maybe this is not as convenient, as efficient as using two different chemical species, but it's working as well. And this was the first implementation of this technique with Fermi gases. And here you see a measurement of a quantity that I was mentioning before, that is the average energy per particle. So at large temperature, so when the gas is classical, so the energy is proportional to the temperature. So this is the equipartition theorem. And so the average energy here is 3 kBT, because we are considering particles in a three-dimensional harmonic trap. But as you cool your gas below the Fermi temperature, so you see that you have a departure from this result. So at large temperature, everything is in perfect agreement with a classical gas, but then below TF, you see that you have some excess of energy. So this energy divided by the classical result is above 1, and this happens because you have the formation of Fermi C. And we have reviewed in the previous lecture that even at zero temperature, the Fermi gas has a non-zero internal energy, because you have the occupation of all the energy levels available up to the Fermi energy. And so even at T equals 0, you expect a non-zero energy. And this measurement is performed with a standard time-of-flight absorption imaging. as that we have considered in the previous lecture. And so you have your gas, and your gas is expanding when you remove the trap, and so you can measure the velocity of the particles. So you can measure the kinetic energy of the particles, and so from that you can extract a direct measurement of the energy of your gas. And so this is the first experimental proof of achievement of Fermi degeneracy in an atomic gas, and you don't have any phase transition, we already told that. And the system changes continuously from a classical gas to a gas in which quantum effects can be observed. And quantum effects can be also observed in the cooling process itself. So let me show a slide. What you see here is the temperature of a gas of fermions as a function of the number of particles during the cooling process. And this data refer to a spin mixture of ytterbium fermions, and this comes from our labs at the Department of Physics. And similarly to what I've shown to you before, even in this case, the sympathetic cooling is realized by using the same isotope but in a spin mixture. And what do you see here? You see that, let's see first the plot on the left. So as the number of atoms is decreased, so the gas is cooled, and here I plot the temperature in units of a Fermi temperature. So during the evaporation cooling, so you have a reduction of the number of particles, and so a lowering of the temperature, but you have here a knee in this curve that happens when the temperature is on the order of Fermi temperature. So when you have the onset of Fermi degeneracy, you have a decreased efficiency of the cooling. And this can be observed more clearly maybe on the plot on the right, where you have the same data, but here the temperature is plotted in absolute units, so nanokelvin, again as a function of the number of atoms. And this plot is in double log scale, so you have a log scale both for the vertical axis and for the horizontal axis. And we studied evaporative cooling, and we saw that in evaporative cooling you have a scaling law of a temperature with a number of particles. So you reduce the number of particles and you reduce the temperature with an exponent gamma that depends on the details of the process. And so you see here that the scaling law is well respected, and this is the line that is fitted to the large temperature points of this data set. And instead, when the number of atoms is around 5 times 10 to the 5, so here, you have a deviation from this fit. And this corresponds to the onset of Fermi degeneracy, and so you see here that this scaling law stops to be valid. So this cooling is less efficient when you have a Fermi gas. So this effect is called polyblocking. Polyblocking is a reduction of a collisional cross-section that happens when you have the formation of a Fermi gas. What happens below the Fermi temperature? You will have something like this. So the occupation of states as a function of the energy will exhibit this familiar Fermi distribution. And so for sufficiently low energy, you have an occupation that is equal to 1. And so all these states are basically completely filled. And since they are completely filled, they cannot be the final states for a scattering process. In a classical gas, two particles can scatter into whatever final states you want, because these states will be available, because in a classical gas, the occupation of the levels is much less than 1. But here, you have some states which are forbidden for the scattering process, because they are already occupied. And so you have this density of states effect, so an effective reduction of the number of states that is available that leads to an effective dependence of the scattering cross-section on the temperature. And so in particular, when T over Tf goes to 0, the scattering cross-section also goes to 0. And here I'm considering the scattering cross-section between distinguishable particles. we know that if the particles are identical, V sigma is always equal to 0. So this is a sigma that would be different from 0 because we are considering a spin mixture of particles, so particles that can be distinguished, but the cross-section goes to 0 because you have this effective suppression due to the filling of the Fermi surface and to the impossibility of occupying these states which are already occupied by other particles. So, great! We can produce atomic Fermi gases. And what can we use these Fermi gases for? So what are the applications of these systems? And of course there are a lot of them, and we have no time to discuss all of them. I can tell you that we will look at some of these applications in the next videos that will be devoted to the physics of optical lattices, and also when we will speak in a couple of lectures from now of optical atomic clocks. And there we will see that the natural absence of interactions in a spin polarized Fermi gas, in which the interactions are strictly zero at low energy, is an important resource if you want to study the physics of a system of particles that do not interact between them. And so we will see these applications. But on the other hand, if you have a gas of fermions in more than one internal state, so you can study the physics of interacting fermions. And the physics of interacting fermions is very important and very rich. Also because, you know, interacting fermions are at the basis of the world. So everything is built upon interacting fermions because fermions are the fundamental constituents of matter. So either you consider matter at the atomic level, if we consider the constituents of an atom, so the protons, the neutrons, and the electrons, or even more fundamentally, if you go at the nuclear and subnuclear scale, if you consider, for instance, the quarks as the constituents of hadronic matter, and so on. Eventually, all the fundamental constituents of matter are fermions. So having a platform where you can study the behavior of a Fermi system, of an interacting Fermi system, and also where you can tune the interactions between fermions, for example, with a flashback resonance, is something that is very useful also from a more fundamental point of view. Speaking of which, I will show you just one application in this video that is related to the possibility of studying condensation and superfluidity of fermions. Here it is. You see here time-of-flight images, so 3D reconstruction of time-of-flight images, where as you cool a system of fermions in two different spin states, at some point you have a condensation. So these images are very similar to what we discussed in the case of atomic Bose-Einstein condensates, but these experiments are made with fermions. And so if you cool your fermions below some critical temperature, you can have a condensations like in the case of bosons. What is the difference? Here you have fermions in two spin states, and these fermions are strongly interacting. So you cannot have condensation of an ideal Fermi gas, but you can have condensation of strongly interacting fermions in two spin states. And this physics is strongly connected with two very important phenomena that were discovered in the last century, that are the superfluidity of helium-3 and superconductivity. In the last lecture, we discussed the superfluidity of helium-4, that is a liquid made of bosons, and below a temperature of approximately 2 Kelvin, you have Bose-Einstein condensation, and your liquid becomes superfluid. Much later, so in the 70s, superfluidity of helium-3 was also discovered. So it was observed that also helium-3, that is a liquid of fermions, can become a superfluid when you cool this liquid below a temperature that is on the order of 2 millikelvin. So much less than the temperature that you had for helium-4. 3 orders of magnitude lower. And the physics is pretty much the same. So there are differences, of course, that I will not touch in any detail, but even in this case, at some point you have a phase transition from a normal liquid to a superfluid phase at these very low temperatures. And the other super discovery of the last century was superconductivity. Superconductivity was discovered even before helium-4 superfluidity, so in 1911, by Kamerlingh-Onnes, that was performing some measurements of electrical conductivity of mercury. So mercury is a solid at low temperatures. It is a metal. As you reduce the temperature, so the resistivity goes down, but then at some point you have a phase transition, so a critical behavior at approximately 4.2 Kelvin, where the electrical resistivity goes exactly to zero. Of course, within the uncertainty of a measurement. But you see here a very drastic change in the properties of electric flow in this material. This is superconductivity. And superconductivity has a lot in common with superfluidity. So superfluidity is the possibility of a fluid to flow without any mechanical friction, so without any waste, any dissipation of mechanical energy. Superconductivity is the possibility of an electrical current to flow in a material without any dissipation of electrical energy because of the absence of resistivity. And the explanation of superconductivity happened in the 1950s, and you have the famous BCS theory by Bardeen, Cooper, and Schrieffer that explained microscopically the formation of superconductor in terms of Bose-Einstein condensation of Cooper pairs. So what are Cooper pairs? Cooper pairs are pairs of electrons with opposite spins. So you have in a metal you have a mixture of two Fermi gases, so electrons with spin up and electrons with spin down. You can have interactions between electrons with opposite spins, and these electrons can pair and so form a couple. So this is not really a bound state, so this is not a molecule. So this is a kind of composite object of two fermions that in some sense acquires a bosonic character. So two fermions for a boson, in particular the Cooper pair has spin 0, and so you can have Bose-Einstein condensation of Cooper pairs. And this Bose-Einstein condensation of Cooper pairs is the microscopic explanation of the superconductivity behavior. And in order to create these Cooper pairs that then can condense, you need some form of attraction between the particles. And this attraction is provided by the crystal. And so you have a kind of second order process in which a spin up electron interacts with phonons, so with lattice vibrations, and these lattice vibrations then interact with a spin down electron, and so at the end you have a kind of effective attraction between the two particles that can create this Cooper pair. Then, if the temperature is low enough, you can have Bose-Einstein condensation of these Cooper pairs. And a similar explanation can be given also for helium-3 superfluidity. Of course, there are differences, but a BCS description can work also in this case. One difference is the nature of attraction between the particles, because for helium, liquid helium, you don't have any lattice, and the attraction between the particles is natural, and it is, you can think to some form of van der Waals attraction for helium-3 atoms, as we have in the case of ultracold atoms. Now, before going back to atoms, let me just show you one important feature of this condensation of fermionic pairs. This feature is connected to the critical temperature. In the case of helium-4, you have bosons, and so the superfluidity happens at the same temperature for which you have quantum degeneracy. And so you have that this temperature is basically equal to the Bose-Einstein condensation temperature. But this is different from what happens in fermionic superfluidity or superconductivity, for which the temperature for superflow is much lower than the temperature for the Fermi degeneracy. That is 5 Kelvin in the case of helium-3, and it is tens of thousands of Kelvin in the case of electrons in a metal. So at the end, this critical temperature for superfluidity or superconductivity is on the order of 10 to the minus 4 or 10 to the minus 5, the Fermi temperature for the system. So this is a striking difference between the two phenomena. So fermionic superfluidity is harder to be observed, and this is very well explained by the BCS theory. I don't have the time to review that. You will do that in the course Gas Quantistici if you are interested. And what you see here is the critical temperature from the BCS theory that is plotted as a function of the scattering length between the particles. The relevant parameter here is 1 over kFa, where kF is the Fermi momentum. And so the critical temperature from the BCS theory can be written as basically the exponential, with some prefactor, as the exponential of minus 1 divided kFa. And so you see that you have an exponential dependence on the interaction strength. And so because of this exponential dependence, if you plug the interaction strengths for helium-3 or for electrons in a superconductor, you find these rather low values of the critical temperature Tc. So in this plot, you are at the very left, so where this exponential is basically almost zero. But then we can extend this theory, and what I'd like to show you is now what happens if you perform a more complicated calculation that extends the validity of the BCS approach to stronger interactions and also to interactions with a different character. And this is what you get. So the BCS theory only works for weak attraction. In a kind of perturbative regime. But here, what happens when this parameter is close to zero is everything but perturbative. So here the interaction strength is very large. So the scattering length is larger than the inverse Fermi momentum, and you can have superfluidity also in this regime. But even more strangely, you can have superfluidity also for positive values of the scattering length that is associated to a repulsive interaction between the particles. Not only, it also seems that the critical temperature can be much larger. So instead of being 10 to the minus 4, 10 to the minus 5, on the right side of this plot, it is on the order of 20%, 25% of the Fermi temperature. And so what the hell is happening here? So why do I have a pairing of the atoms also in the case of repulsion between them? Because I can understand this physics of Cooper pairs formation and condensation if I consider an attraction between the particles. So why should I have it in the case of repulsion? So what is the mechanism that leads to the formation of bosonic composite objects? So the physics is rather complicated, and it cannot be explained just in half an hour. So it needs a lot of discussion, and we cannot do that. Let me just give you a feeling for that, or in other words, let me try to make you curious about this kind of phenomenon. In order to try to explain what's happening here, let me tell you that this happens when the interactions within the particles are strong, and in particular it happens when you use a Feshbach resonance to change the interactions between the fermions. And these images refer to the condensation of fermionic pairs when you have a repulsion between them, and in particular when you have a strong repulsion, so for very large values of positive scattering length. And if you look at the text in this slide, you see that here I have written fermionic molecules. So let me now just tell you this point. Why are we talking about molecules? In order to explain that, we should go back to the physics of flashback resonance that we have discussed some lectures ago. So I just remind you that in a flashback resonance, you have a resonance of the energy of a scattering state of two fermions that are colliding with a bound state of these two atoms in a different collisional channel. So different spin states that correspond to different interaction potential, and you can have a bound state of this closed channel potential. And this bound state is a molecule. And when we studied the dependence of a scattering length of a scattering state on the position of this bound state, we performed some calculations in which at the end, so the core of that calculation was a diagonalization of a 2x2 matrix in which we considered the two scattering channels, so the open channel and the closed channel. So in the open channel, you have a scattering state, and you consider an energy 0 for this scattering state, so the low energy limit for scattering. And then for the closed channel, instead, you consider this bound state. And the energy of this bound state can be tuned by applying a magnetic field. So taking advantage of a difference in magnetic dipole moment of the two channels. So by changing the magnetic field, you can change the energy of this bound state, EC. In particular, when B is equal to B0, you have the resonance, and so you have a resonant enhancement of scattering cross-section because of the presence of a bound state. So the energy of a bound state is the same as the energy of a scattering state. And this happens because you have a coupling between the two channels, and this coupling is provided by the hyperfine interaction, as we have discussed in the lecture on flashback resonances. This is exactly the same physics. Now, instead of performing the calculation of the scattering length, we can do something that is even simpler. So you can just take this 2x2 matrix and diagonalize it. So without writing wave functions and nothing like that. So very simple, very easy. So we take this 2x2 matrix and we diagonalize and we find some eigenvalues. So it's just a very quick calculation that you could check. So these are the eigenenergies which correspond to this Hamiltonian. And if we plot them, you find the energy spectrum as a function of a magnetic field that is shown in this plot. And you have two solutions, so you have two branches for the energies. And let's first consider what happens in the two limits of a magnetic field that is much larger than the resonance field and much lower. So when it is much larger, the lowest energy state is given by the scattering state in the open channel, because here the molecular state in the closed channel has a larger energy. But it becomes the opposite when the magnetic field is smaller than B0. So when it is smaller than B0, now the bound state in the closed channel has a lower energy. But the two channels are coupled, and so here when their energy cross, you have an avoided crossing, and so basically in this lower branch, you have a continuous change in the character of a low energy solution that interpolates from the scattering atoms in the open channel down to the molecule in the closed channel. To be more precise, if we recall the analysis that we did in terms of scattering length, we find that for B larger than B0, the scattering length is negative, so attraction between the particles in the scattering state. Instead, for B lower than B0, the scattering length is positive, but this positivity of a scattering length refers to the scattering state that is not the lowest energy solution for the problem. So in some sense, the scattering state for positive scattering length is the upper branch. So it's a kind of metastable state. The lowest energy state in the problem is the bound state, that is the molecule formed by the two fermions, and so there is no contradiction in that. So you can have a strong bound state even if you are considering a positive scattering length. So this physics is quite complicated, so don't worry if there are things that you don't understand. It is natural. Just want you to give you a flavor of what's happening here. Just try to understand this. When we have this flashback resonance, the system of two fermions can change continuously between fermions with attractive interaction to a bound state, so to a molecule of these two fermions in the regime where you expect a positive scattering length. But don't be fooled by that, because this positive scattering length refers to an excited state solution, not to the lowest energy state that you are considering. So, crossover from fermions with attraction to a bound bosonic object. And let me just show you the last couple of slides. So I will go back to the presentation. So this is why I talked of fermionic molecules here. So this is really Bose-Einstein condensation of a bosonic object made by two fermions. And what happens here in this regime is really the physics of Bose-Einstein condensation. And there is this picture that is completely qualitative, but it gives you the idea of the crossover between the regime of positive scattering length, in which you have Bose-Einstein condensation of these tightly bound molecules, to the regime of attraction between the particles when you have the BCS theory that is working. So, in the BCS theory, you don't have Cooper molecules. Cooper pairs are just atoms that have some correlation between them because of attraction between them, but you don't have a real bound object in physical space. So here you have tightly bound molecules. So these are molecules that are just a few nanometers in size. In the BCS state, you have correlations between particles that are mostly correlations in momentum space, and so the size of a Cooper pair can be very large. And you have superfluidity in both the situations. So both for the case of Bose-Einstein condensation of molecules and in the case of condensation of Cooper pairs. But you have superfluidity also in the middle. So when interactions are very strong, and so here you have a regime that is called the crossover regime, or in other words, it is also called the unitary regime, because of some properties of the many-body state that I will not touch in any detail. So you have always this superfluidity. So in particular in this intermediate regime, so these here interactions are very strong, and so basically you have everything that is interacting with everything. So it's kind of a very complicated system where interaction between the particles are at the strongest, that are possible. And the details of the superfluidity will change. In particular, we have seen that the temperature depends on the regime. So you have BCS with this kind of weak form of superfluidity with very low critical temperature due to the Bose-Einstein condensation that you have instead on the other side of a plot. This kind of crossover between the two regimes, BC and BCS, is called the BC to BCS crossover. You don't have any phase transition between these two limits, just a continuous change in the properties of your fermionic superfluid between the two regimes. And as a last slide to show you this, I can show you that, for example, you can probe the superfluid nature of these fermions if you rotate your Fermi gas, and you can look at the formation of quantized vortices. So whether you have a BCS superfluid, so with an attractive interaction between the particles that form Cooper pairs, or you have a Bose-Einstein condensation of bosonic molecules made by two fermions, or you are in these very complicated regimes of everybody interacting with everybody, everywhere. If the temperature is low enough, these fermions can form a superfluid state, and you can observe very nice, very beautiful quantized vortices for all the interaction parameter strength. Okay, so again, don't worry if you don't understand something of this explanation that was very fast and very introductive. So in these last lectures, I'd like to give you some feeling of some important contemporary topic of research. So of course, each of them would have to be developed in a separate course. So don't worry, this is not the purpose of these last lectures, but I'm happy if you have, if I was able to give you some feeling and some intuition of the kind of physics that is happening here. So physics of superfluidity and superconductivity that can be studied in a system of cold atoms in which, last minute, you can change this interaction parameter. So this is what you cannot do with either helium-3 or electrons in a superconductor. You cannot adjust this critical temperature. So this is fixed by nature. And so there is little that you can do. So you can study, of course, the systems that can be formed, the kind of superfluids that are naturally formed in these systems, but you cannot achieve this regime that was possible to study only with cold atoms, because of this possibility of changing the interaction between the particles with this Feshbach resonance in order to have this strongly interacting regime. That's all. I have discussed a lot of things about fermions, and this is really now the end of this part of the course on quantum gases. And so in the second part of this lecture, so in the next video, and also in the lecture after that, I will discuss the topic of optical lattices. So thank you for watching. See you for the next video on optical lattices.